Hello everyone, I'm here to present our work machine learning based fine-grained modeling of DC current coding in power delivery TSVs for face-to-face 3D IC. Here is the outline of this presentation. First, I will introduce the background and previous work. Next is the motivation that why we need to use graph attention network. Then I will introduce the methodology of our framework. Finally is the experimental results and the conclusion. For this slide, I will introduce the current coding effect. In face-to-face 3D ICs, power TSVs provides connectivities between the power delivery network of two tiers. As shown in Figure 1a, the ground TSV connects the VSS bump to the lower ground rail in the face-to-face 3D IC PDN, conducting a significant current across two tiers. High current flow can lead to large airdrop and EM aggregation. In static airdrop analysis, TSV parasitics are typically modeled as a single resistor. This modeling assumes a uniform current distribution across a TSV, which simplifies the actual scenario. Due to variations in the cross-sectional area of via ladder, TSV landing pad, and TSV pinner in face-to-face 3D IC, the current coding distribution changes as it passes through the interface between two components. Figure 1c illustrates the current non-uniform distribution at the interface between the TSV pinner and the TSV landing pad. This current coding effect in TSVs further increases the overall airdrop of the chip as shown in the red figure. Therefore, it is crucial to account for these effects when analyzing 3D IC PDNs. Previous studies have investigated the current coding effect in face-to-back 3D ICs. When current coding typically occurs in the region where the current undergoes a 90-degree shift. In contrast, the face-to-face 3D IC scenario is different. As shown in Figure 1, current coding primarily occurs at the interface between the TSV and the via ladder. Figure 2a shows a top-down view of the TSV landing pad and power rails. There are two primary ways for cell current to flow to the landing pad. One path involves current flowing through the lower power rails to the side of the landing pad, while the other involves current traveling from the upper power rails through the via ladder to the landing pad. We compare the resistance of these two paths across different cells, with experimental results shown in Figure 2b and 2c. The findings indicate that the majority of the current flows through the via ladder. Therefore, this work focuses on the current coding effect induced by current flowing through the via ladder. Finite element analysis is one of the most important methods for analyzing current distribution within TSVs. However, obtaining a fine-grained current distribution using FEA can take over 1 hour, making it impractical for large-scale applications. To address this limitation, previous work proposed a TSV resistor model to compute the current and voltage distribution within TSVs. This method segments the TSV structure into a 3D mesh of cubic elements, where each cube contains multiple resistors, forming a fine-grained resistor network. A circuit simulator can then be used to solve this network and obtain the current and voltage distribution. Compared to FEA, the TSV resistor model significantly reduce the simulation time from hours to just a few minutes. However, its accuracy is limited in the regions with severe current clouding. Additionally, despite the speed improvement, the simulation time remains a challenge for large-scale applications. Therefore, our work proposes a graph attention network-based framework to obtain fine-grained current and voltage distribution. Graph attention networks offers several key advantages. First, the self-attention mechanism allows JT to extract useful information from graph structures. Second, the multi-head attention enhances JT to process multiple types of features. Third, JT effectively mitigates the accuracy aggregation caused by the cube discretization in the TSV resistor model. As a result, our JT framework achieves highly accurate predictions of current density and voltage distribution with an inference time of just 2 to 3 seconds, making it significantly more efficient for large-scale applications. This work aims to develop an end-to-end supervised machine learning framework for predicting the current density and voltage distribution within TSVs. Our methodology consists of two main parts. First, we propose a method to transform the irregular TSV structure into fine-grained graphs, enabling effective graph learning. Second, we design two GAT models. One model predicts the 3D current density distribution, while the other predicts the 3D voltage distribution. Next, I will introduce these two main parts in detail. To construct fine-grained graphs, we segment the TSV and landing path into a 3D mesh cube network based on the TSV resistor model method. We then represent the structure as a graph, where resistors are converted into edges and their terminals into nodes. Therefore, edge labels correspond to current density, while node labels represent voltage. Each node and edge are assigned a feature vector containing rich structural and electrical information. The fundamental features of nodes and edges are summarized in Table 1. To enhance feature representation, we introduce two structural similarity matrices into the edge feature vectors. Global structural similarity score evaluates the similarity of neighboring nodes shared by two nodes. Local structural similarity score evaluates the similarity of two neighboring nodes. These matrices are designed to capture the structural characteristics of the graph more effectively. By integrating these feature vectors and enhancement techniques, our fine-grained graph representation enables the model to learn more detailed characteristics of the TSV structure and its electrical properties. Since predicting voltage distribution and predicting current density distribution are different tasks, we designed two different JT layers with different aggregation methods. Each JT layer incorporates both node aggregation and edge aggregation, forming what we call an edge node graph attention layer. For current density distribution, edge information is more critical, therefore we prioritize edge aggregation, where the attention scores are used for edge feature vectors. For voltage prediction, node information is more relevant, thus we perform node aggregation first with attention scores used for node features. We use two different JAT models for edge prediction and node prediction. For each prediction task, we use four edge node graph attention layers to extract information embeddings. The embeddings from each JAT layer are concatenated for final embeddings. The current density predictions we use edge embeddings, while for voltage predictions we use node embeddings. Finally, we employ an 8-layer MLP to decode these embeddings and produce the final outputs. Next, I will describe the experimental setup used to train and evaluate our models. For the training dataset, we consider 4 key variables as listed in Table 1, resulting in 108 possible combinations. For each TSV structure, we construct a fine-grained graph which contains thousands of edges and nodes. The statistical summary is listed in Table 2. To generate ground truth data, we use commercial simulation to access Q3D to obtain the current density and voltage distribution for all 108 TSV structures, requiring a total simulation time of 74 hours. We randomly split the dataset into training dataset, which contains 87 graphs, and testing dataset, which contains 21 graphs. The edge prediction model is trained for 3000 epochs, requiring 33 hours, while the node prediction model is trained for 8000 epochs, taking 33 hours. This slide demonstrates the accuracy of our GAT-based framework. Figure 1 compares the predicted current density and voltage values against the ground truth in the test dataset. The coefficient of determination is 0.97 for edge prediction and 0.99 for node prediction, indicating high accuracy in both tasks. Figure 2 illustrates the current density and voltage distributions across selected cross-sections. The predictions display good symmetry, further validating the effectiveness of our approach. Overall, these results confirms that our GAT-based models accurately predict the 3D distribution of current density and voltage. In this section, we compare the prediction accuracy and inference time of our GAT-based models against other machine learning-based and non-machine learning-based methods. To evaluate the efficiency of our GAT architecture and propose aggregation methods, we compare our models with EM graph, a graph convolutional network, and a MLP model. For both edge prediction and node prediction, our GAT-based models achieve the highest accuracy, demonstrating their effectiveness in handling complex graph structures and feature vectors. Additionally, we compare our GAT-based models with the TSV resistor model method. Our approach achieves higher accuracy in the current density prediction task and offers faster inference speed across both prediction tasks. Finally is the conclusion. We investigate the current crowding effect in face-to-face 3D assays. We also propose a method for constructing fine-grained graphs based on TSV structures. Then we design a supervised GAT-based framework for accurately predicting current density and voltage distribution. Finally, we demonstrate that our GAT-based framework outperforms other machine learning-based methods and non-machine learning-based methods. Thanks for listening.